Good.
Hi guys, I think we're running a bit late, so I'll try and be as quick as I can. So this work is based on the idea that there are a lot of problems that it's not entirely clear whether they're planning problems or scheduling problems. The more complex real-world scheduling problems, you've got choice about what it is you're scheduling. And so what we're trying to solve is these hybrid problems. And how we do that is by combining these sort of three techniques, because planners don't like having to wait for other people, because the delete relaxation says, hey, it was clear at one point, I can continue using this resource forever. And schedulers, and in particular we're using mixed integer programming, don't like having to guess how many resources you have to use. And we also use domain control knowledge in the form of a Golog program, and that is actually the specification of the problem. So we solve this by decomposing the problem, which is common in OR and a lot of optimization fields. It allows you to scale to much bigger problems. But we do it in such a way that we retain optimality. So what do I mean by a hybrid problem? So I'm going to be talking about Rails stuff, because it's the motivating example that inspired this technique. But basically, hybrid problems have these independent subtasks that are coupled only by shared resources. And that sounds an awful lot like scheduling. And in the first picture, you're scheduling which train goes first and that kind of thing. But we've also got a choice of how to achieve those sub-goals and when we want to achieve them. And that's a bit more like temporal planning. So we want to try and use the strengths of both of them. Now, this was actually, so this is the problem that I'm going to be talking about, and this is one that I've solved in industry. And schedulers can handle this class of problem, but you tend to get really fragile models. So if you can see between the D and the Y in there, somebody put another port. So the M's are mines and the P's are ports. We had a business process change for a client for a company I work for in Melbourne. They built a port between the yard and the depot, and it took me 9 months to fix, because the scheduling solver had so much pre-processing that was all very domain dependent. So I wanted to try and use planning. And so the problem specification's on the right. This is in the form of a Golog program. Now to read that says run a service for order 1 on consist 1 concurrently with running a service for order 2 on consist 2. Now an order is just a set of points. So I'll go through the first example. So order 1 is just you start at the yard, go to the depot, to the mine, back to the depot, to the yard, to the port, and then you refuel at the yard again. That's basically all we're trying to do, but we're doing it for a concurrent set of these orders that all share the same track network. Now, we can see that the depot there is a kind of a bottleneck, even though it doesn't show up anywhere in our definitions of our orders. These orders all have time windows as well, so that's what makes this a hard scheduling problem. So you've got to pick up the coal from the mine on Tuesday, and you've got to deliver it on Tuesday, or you've got to pick it up on Tuesday and deliver it on Wednesday. So to run a service, you iterate over all the locations, you wait for some period of time optionally, and then you try and go there. So this is kind of a hierarchical kind of idea. So what we have is I've bolded all the primitive actions. That's all you need to know. Hopefully you kind of understand the domain at this point. It's very simple. You're just trying to schedule a bunch of trains over a track network, but you don't know which bits of that track network each train is going to use. Okay, so I've explained the domain. I'm going to explain how we're going to model it. We're going to model it as a MIP, sort of. A MIP where all of the possible plans are a column, are a decision variable. This is an idealized version. We don't actually solve it this way, but if we think of it like this, you have to minimize the cost of all those running those trains, subject to the constraint that nobody is overusing any resource. And in this domain, a resource is a node on the track section, on the track network. So you can't have two things at the depot at the same time, with the exception of the yard, because there's loads of siding, and you all start there. You've got to have enough space where everyone starts. So yeah, this is the optimal solution to this MIP is an optimal solution to your temporal planning problem. If you had all of the individual trains plans with the correct timings and everything, so at time 1 I'm on this track section and so on. If you just find the set that minimizes the cost without violating any of those resource constraints. So how do we do that? You've got an exponential number of those possible plans for each of those trains. You can't possibly enumerate them, but we don't have to. If you know anything about how the simplex algorithm works, what you're trying to do at every node is you're trying to find the decision which has the least reduced cost. And what reduced cost means is it's an estimate that's accurate at a specific point in the search space of how much making a decision can improve your objective. So what happens is reduced cost is denoted gamma here, as that gamma function. But basically, every constraint in your MIP, which is a resource in your planning problem, a shared resource, has a dual cost. And that tells you exactly how much making that decision affects the other agents. And so as you iterate and generate a plan, and so all you have to do is basically you have to pick the next train, the next candidate schedule that has the least reduced cost, the most negative reduced cost, until no such columns exist. And once no more columns with negative reduced cost exist, you've found the optimum. So we use this idea. We don't actually need all of the columns in advance. We just start with some feasible subset, solve this linear program, and then we search for a new negative reduced cost plan from each of our agents or sub-goals. Now this means, obviously, you may see a problem with this. How are you going to start off with a feasible joint plan if the point of this is having a feasible joint plan? So what we actually do is, the first thing we do is we turn it into an oversubscription planning problem. So all of the goals are relaxed, and now we're trying to find, we keep iterating until all of our agents, all of these sub-goals say, my best plan is to do nothing. And as soon as you get to that point, you've found the optimum. So basically, you start off with no plans, you find the duals for all of your constraints, and you iterate, and you'll find an optimal plan. Hopefully that makes sense to some people. So this is exactly what the simplex algorithm does under the hood. So I'll walk you through an iteration of this. When you start off, there are no duals. So you start off with basically no resource costs. So this is effectively, each train is assuming it's the only train on the network. And so what they both do is we ask them for their optimum plan, and they go, okay, I'll leave straight away and head to the depot. And I'm counting at the bottom all the resources they're using and the current value of the dual for that. Those duals are global, but I'm just putting them on both sides because they will diverge in a second. And now they go to their respective mines that they want to go to, and they add some more resources to their plan and their costs. And you keep stepping through the network until you get to the end. So they've gone from the yard to the depot to the mine, picked up the coal or iron ore, and then headed back to the port, dropped it off, and then back to the yard and refuel. So, and at the end, we use a resource that is, you can only deliver a given order once. So that's just a special resource there. So at the moment, those have both got length 8. They've got, assuming unit cost, total cost of 8. But they crash at the depot straight away. That's kind of bad, right? Trains crashing is bad. So what happens is the duals get updated. So now the LP computes that being at D at time 1 is costing the global solution this negative big M plus 8 is the maximum improvement you could have by having fewer things on that D. So in the next iteration, instead of leaving immediately, both trains leave at time 1 and therefore avoid that massive penalty cost that they would have had to have paid. And they, again, just basically offset by 1 time unit. They go to their respective mines, pick up some ore, head back to the depot, to their port, unload, head back to the yard, and refuel. Now, at this point, again, we update the duals, and we discover that this had cost 9. So what we now discover is that, I've forgotten to update one of these. Ignore that 8 minus M, that's supposed to be a 0. We discover that delivering each order is now costing you 9 units. Basically, because everybody's already got a plan for how to deliver that order, The fact that there's two of them is the bottleneck. But also we see that there's one extra unit of dual cost on being at D at time 1. And now if you try and search with these additional costs, you'll find that there's nothing that has reduced cost below 0. And that's proved optimality for this very small example. So this is all well and good, but how does this compare against normal schedulers that aren't hybrid and normal planners that don't take any hybrid approach? So we compared against an existing implementation of temporal Golog, which is just trying to effectively do theorem proving. PopF2, which is the only temporal planner that could actually model the time window constraints from IPC 2011. CPX, which is a state-of-the-art resource-constrained scheduling solver. It's constraint programming, but it is state-of-the-art for a lot of resource-constrained scheduling problems. And our approach. So each of these kind of has a different model, but they're all equivalent models. So we see this is a half-hour timeout with 4 gigabytes of memory. We didn't expect the temporal Golog to do anything special because it's a theorem prover. But PopF2 really struggles when it's trying to schedule more than 4 orders. And you'll notice the number of vertices is the first column, so that's how big the track network is. Most of those are exactly that network that we just saw. The ones at the bottom are simplification of Rio Tinto's real track network. The number of orders is increasing exponentially in that main part, and the number of mines per port that a given port takes orders for. So that's kind of a measure of the fan-in that happens at the port. How many different orders are trying to get to the same port at the same time. So we can see that FPP keeps scaling to 256 of these happening concurrently, and it solves that in about 10 minutes. Whereas most of the other ones take half an hour to solve anything more than 4. So time windows are hard. Maybe we just encoded those time windows badly for temporal planners. To make sure that wasn't in fact the case, we relaxed them and tested it against a wider range. Now, it should be noted that this problem is trivially polynomially satisfiable without time windows, because you can just do exactly what we did, one after another, running one train at a time, and it's very, very easy to get these plans. So using this, we could try it against, in addition to PopF2, YASP2 and CPT4, both of which were in the last temporal track IPC. And I've skipped most of the table because it's no different past that last line. But again, we see that none of them really scale past about 16 orders. And this is time to first solution, by the way. So by using heuristics, you can actually get to time to first solution. There's not a huge time difference between first solution and optimal solution, but it can take a while to prove it, which is why we've put it there. Now, obviously, this is a very applied domain, and if it could only solve one problem in the world, that wouldn't be so interesting. So we worked out how, we've got an example in our paper, and this is it, on how to do basically a multi-agent version of blocks world. So you've got as many arms as there are blocks, and you're just trying to maximize your concurrency effectively and put them all down as quickly as possible. So the clearness of a block can be used as a resource, and this is now a resource that can be generated. And that's a little bit different than what I've described before, but fundamentally the same algorithm happens. And read the paper if you want the details, because I've only got 4 minutes left. Basically, a fragment in this case is the actions on a single block. And so, funnily enough, the planners were really good at blocks world because they've been doing it for 40 years or something. And so, time to first solution, we've got nothing. But as this is an anytime planner and these are a bit easier problems, we also ran it on time to optimal solution. And CPT is an optimal planner, so it beat us on pretty much all of those, except the very largest one. The idea of this work is that it's designed to scale to bigger things. So the fact that it's that fragment-based planning can prove optimality faster on the biggest instances, that's useful. These aren't huge. These are just the ones that were in the 2011 sequential track that I just made temporal by adding more arms. So yeah, basically what I want you to take away from this is that FPP is an interesting new technique that kind of tries to bridge the gap between planning and scheduling by using a planner inside a scheduler, or arguably, deriving a scheduler from a planning specification. It allows you, to write these planning-like action language models in Golog that then you can derive complex scheduling algorithms from. There's lots of engineering improvements here. This planner was written entirely in Python versus all of the C++ implementations that it's being compared against. So most of those small cases are constant factors from being compiled versus not, I hope, I think. But yeah, and we need to do some more work on how to make more general models from this, because I had to write these in quite a different formalism from strips, but I'm currently working on what the necessary and sufficient conditions are for a correct model for this formalism. And also, because you're solving this subproblem usually hundreds of times, and the only difference in each of those subproblems is your action costs. There's a lot of space for applying learning and other clever techniques to speed up the fact that you're solving essentially the same problem lots and lots of times, particularly with no goods, and I'm working on something like that at the moment. Cool, I finished early. Success.
Any questions?
So maybe I missed this, but I'm quite curious. What did you perhaps try writing an integer model with 0-1 variables, which would allow you to say things like only one train can be in the depot at any one time?
That's exactly what I did, effectively.
But it looked like, okay, effectively. So,
but what this is effectively a Danzig-Wolff decomposition of that model. The problem with that is you don't know how many time steps you need to solve this problem. Particularly with the 256 case, that's got a make span of about 1,000 and 3,000 applicable actions, 3,000 actions in the final plan. So if you start adding 3,000 time steps to a MIP model for this, it can be quite big, and just formulating the problem can take 5 minutes.
okay, so you mean doing a direct integer program representation where you'd formulated your time points and your 0-1 variables would be too big to solve?
Yeah, and even just the fact that you have to iterate over all the time points, and it's quadratic on each of the time points, I think. So you end up with this huge model that's got flow variables everywhere. Mm-hmm. So yeah, it can be quite slow.
Okay, thanks.
Also, you can't write it as a planning model, which was the point. So the idea is you want to have something that's a flexible model. So I wrote that as a Golog program, and the MIP model fell out. Yeah.
More questions?
So as far as I understood it, the pricing problem you're solving with your own Python implementation, can you just use a planner?
Yes, but you end up with the subproblem that it induces has time-dependent costs. And it's just this sort of stepwise cost function that most planners, well, in strips you'd have to propositionalize over time. And so you really don't want to do that, funnily enough. So yeah, I'd like to be able to use a planner for that, but at the moment you can't specify those kind of cost functions in an off-the-shelf planner.
Okay, we're running late, so there's a lot of people who want to talk to Toby, I think, so if you can catch him during the breaks or during the rest of the conference. Yep. Thank you very much.
Thank you.